All right, cool. I think we're a minute or two at the top of the hour, so let's go ahead and kick off, shall we? And so, good morning, good afternoon, and good evening, however the day may be greeting you. I think the majority of you might be a little bit ahead of me. It's 8 a.m. here in the Bay Area, so thanks for taking time out of your busy day to spend the next 90 minutes or so with us. If you're looking for the YugabyteDB Fundamentals community training course, you are in the right place at the right time. I want to thank Karen and the folks at the meetup, the Cloud Study Group, for setting this up. It's super awesome that we're doing this, and there's going to be a lot to learn, I think, in the next 90 minutes. Hopefully you find it as instructive and useful presentation. All right, so let's do some welcoming and some housekeeping on the quick. My name is Jimmy, last name is Guerrero. That's the name they gave me. I do developer relations here at Yugabyte. Previously, I was an early guy at MySQL. I was like employee 35 or something like that. I was also at Oracle. I was a founding member of the Red Hat OpenShift team, as well as I did some time at InfluxDB. So I've been kicking around databases since the late 90s. Databases and open source primarily. And distributed SQL, without a doubt, is one of the more exciting things that has been coming up on my radar here lately. So I'm super excited about distributed SQL. That's why I'm at Yugabyte. And hopefully by the end of the next 90 minutes, you'll start to understand kind of the power and potential for transformation that distributed SQL holds for us. All right, let's start with some quick questions and answers. The first one is going to be, let me double check here. Okay. Okay, you can hear me. Some quick questions and answers. The first one, if you joined up early, I already mentioned this. You want to sign up for the Yugabyte community Slack, and you want to join the training channel. That's where we hang out, and we can answer all your questions about any of the material that's presented in this course, but also if you have questions about the exam, where's my certificate, where's the prep, do I get a recording, all that good stuff. Ask those questions in there. That way we can take conversations one-on-one if we need to, and we can archive them. The other thing that I mentioned, if you haven't already seen it, is make sure to vote for a charity. So if you're attending, just follow that link, register, and we've got 3 charities there that are worthwhile. We'll donate $5 on your behalf, so just do that. It's quick, it's easy, it distributes the love, so to speak. Okay, so now some quick FAQ here. Is this course being recorded? Yes. Will I get a link to view it later? Yes. Will I get a study guide? Yes. When can I take the exam? Probably within the next 24 hours after the conclusion of this, because I don't want to hit you with a bunch of emails and a bunch of random stuff. I want to get everything to you and in one communication. So I want to get you a link to the recording, a link to the study guide, and a link to where to take the exam. I want to do that in all one shot. So we'll do it in less than 24 hours. It'll be quick. When can I take the exam? Yeah, so within the next 24 hours, you'll get the link and you'll get all the materials that you need to be successful on that exam. How many times can I take the exam? As many times as it takes to pass. I think most people are just going to pass it on the first time. If you're paying attention, if you do a quick read and a quick study of the exam prep guide, you'll do well. If I pass, when do I get my certification and my badge? Give me about 24 to 48 hours after you complete the exam to create your certificate, get you your badge, and email that over to you. But it should be a pretty quick turnaround. Are there more trainings scheduled? Yes. And at the conclusion of the presentation, I'll walk you through some of the other courses that we are making available in the future. Best bet is if you want to stay connected, just keep watching what's happening in this particular meetup, and Yugabyte will be funneling all its new courses through this meetup if they're going to have us again. And so this will be the first place that you'll be able to experience those trainings. All right, next up, prerequisites and an FAQ. So if you look in the meetup description, and there's probably, if you're in the channel, I posted the link as well. There is a GitHub page that's got training preparation and FAQ. And really the only hard requirement is that you join the Slack channel, because that's the best way to get your questions answered in as near real time or one-on-one as possible. The rest of the stuff that's on there at the end of the day, it's not mandatory, right, for the next 90 minutes. But if you did go through the process of installing the software, setting up a sample database, and maybe setting up an admin tool like pgadmin or dbeaver or Table Plus or something like that, and playing around with the sample database. What we're going to run through in the next 90 minutes is probably going to give you a lot better context. You'll just kind of have a better idea of how the shell works and the different services and all that good stuff. Not mandatory. I think most folks will get it as we work through the material, but it's kind of a nice thing if you did that, because a lot of the stuff will say, oh, that's why that works that particular way. So the FAQ is there, and the prereqs, just check either the channel, I posted it there, or in the meetup description. That should be there as well. Okay, what are we going to cover in the next 90 minutes or so? The main sections are going to be, we'll cover terms and definitions. This makes sure that we're kind of all speaking the same language. And then we're going to look at YugabyteDB architecture. So we'll do a high-level overview, and then we'll double-click on each of the various components and the role that they play in putting together a distributed SQL system. The other thing that we'll do is that we'll then double-click on the YSQL API. We'll then go through some exercises, and in the exercises, we'll do a local installation. We'll wire up a third-party tool. We'll set up a sample database. We'll create some objects and queries. We'll look at user management, database, and schema management. We'll create a function. We'll create a trigger just to kind of show you how the procedural stuff works. And then we'll do some fault tolerance testing. So we'll set up a 3-node cluster. We'll bring a node down. We'll bring it back online, and then we'll scale one out by adding a 4th node, so you can kind of see how that works. And we don't have enough time to do a TPCC benchmark, but I'll walk you through the steps. It's super simple, and I'll show you what the outputs look like. So if you want to do benchmarking exercises, I'll kind of give you a head start on how to make that happen. And then we'll get to some next steps. So let me turn off my phone here because it is beeping a lot. Okay, and that's what we got. So lots to cover. Don't worry, there's lots of repetition, not a lot, but there's enough repetition built into the presentation where it'll start to sink in over and over again, and it'll also give you a clue, hey, maybe this is going to be on the exam. So you don't need to take screenshots, you don't need to record, you don't need to take copious notes, you just need to be present. The preparation guide or the exam prep guide is going to have everything you need to know in a super simple layout in a PDF. It's going to be fantastic. So just sit back, enjoy the ride, and kind of soak it all in. All right, let's get started with terms and definitions. First, what is distributed SQL? And there's five strong characteristics, right? If you want to consider something as distributed SQL. The first one, and it's probably the most obvious because it's in the name, is that the system has to have a SQL API, right? Not kind of SQL, not fake SQL, but an ANSI compliant SQL API, right? And what I mean by that, or kind of a litmus test for that, is that if I've been using MySQL for many years, or Postgres, or Oracle, or DB2, or something like that, I should, at the end of the day, be able to take 90+% of my SQL development skills and take them to another platform. Granted that each database kind of has its own proclivities about how it deals with clauses or behaviors or things like that. But at the end of the day, if you know SQL, you know SQL. It's just about learning that last 5–10% of what's unique about that particular system. And the expectation, I think, as a developer or as a user should be exactly the same. If something is claiming to be distributed SQL, then I should be able to just take my SQL knowledge and start using it, and not start to have to learn all this new languages and clauses and syntax just to get the functionality to work. So a SQL API is kind of a hallmark of whether or not it actually is a distributed SQL system. The second is going to be distributed data storage. And here we mean automatic distributed data storage. And what I mean by that is that I, as a developer, I just want to put data into the system. And I don't want to have to think or specify, well, this data goes there and this data goes over there. And then when I want to retrieve it, I have to get that data from here and that data from there. And then I have to compile it and put it all. That is not a distributed SQL system. That is something that you're doing a lot of extra work to try to make it seem like that. But at the end of the day, a distributed SQL system, as the name implies, should automatically distribute the storage or distribute the data, right, appropriately based on your node count, based on your replication factor. I, as a developer, should not have to deal with that complexity. That's kind of the whole point of a distributed SQL system. The third point is going to be that just because the system is distributing the data inside of the cluster, I want to make sure that it's being replicated in a strongly consistent manner, right? So this is a sharp demarcation between eventually consistent systems, right? And this is kind of a hallmark of NoSQL systems, which is that yes, they distribute the data, but they do so in an eventually consistent manner, meaning that depending on what node you talk to, you may get an inconsistent view of data. Whereas in a distributed SQL system, there is always a single view of the database, regardless of from what node you talk to. And that's the same expectation, right, that you would have if you were connecting to MySQL or Postgres or Oracle or something like that, right? That you want to make sure that there is always a consistent version of the database, regardless of what client is talking to it. So SQL API, automatic distributed data storage, as well as when you're distributing that data, that it is strongly consistent, right? The fourth characteristic of distributed SQL is going to be distributed query execution, right? Because it's no fun if the system automatically distributes your data and replicates it in a strongly consistent manner, but then forces you, the developer, to then figure out, okay, I want to do select or an insert or a transaction. Now I have to figure out where all the data is. I got to pull it all together. I got to parse it. I got to manipulate it however I want. And then I got to return the results. Nobody wants to do that, right? It kind of defeats the whole purpose. You want basically a distributed SQL system to appear to you as a developer as MySQL or Postgres or some sort of a monolithic system where all of that is abstracted away from you. So that distributed query execution is something that is handled by the system. And the fifth and final point is going to be that you want to make sure that the system is going to offer distributed ACID transactions. So you have the expectation, right, that MySQL or Postgres or Oracle or SQL Server, that when you do a transaction that it's ACID compliant, right? That's kind of the nature of the beast when you're dealing with databases that are for systems of records, right? You want ACID properties. And the expectation should be exactly the same when you're dealing with a distributed SQL system, is that you don't want to relax these principles here, is that yes, I'm doing a distributed transaction, and on top of that, I want to make sure that it's going to be have ACID properties, which of course is a very difficult problem to solve. But that's the magic, right, of distributed SQL. So those are the 5 core characteristics of what a distributed SQL system is. So what's the soundbite? In a nutshell, a distributed SQL database automatically distributes and strongly replicates data so that SQL can be executed against it in a distributed and ACID compliant manner. That's the sharpest, crispest description that kind of encapsulates those 5 characteristics about what distributed SQL is. Okay, I did see real quickly at a glance that we had a question about, okay, well, how is this different than NoSQL? So I did touch on a few of these points, but let's make it real sharp. On the left-hand side, we've got our characteristics, right, of what distributed SQL is. And let's look at how NoSQL is and isn't, or does or does not exhibit these sorts of characteristics, right? With a SQL API, we already discussed that a distributed SQL system, as the name implies, has to have a SQL API that's ANSI compliant, that as a SQL developer, I should be able to quickly understand how everything works or how to program against it. NoSQL systems, depending on which one you're working with, are either going to be semi or non-relational, right? That's the name, NoSQL, right? Is that they relax the sorts of expectations that we have around SQL in order to give you other things like performance and scale and all that good stuff. And you don't have to model your data or anything like that, right? Just 2 different use cases. But I think it's fair to say that NoSQL systems are not going to be thought of as ANSI compliant SQL with stored procedures and things like that. Distributed data storage, we already talked about how that should automatically happen in a distributed SQL system. And in NoSQL, that's going to be automatic or manual. It kind of depends on the system that you're using. Replication, inside of a distributed SQL cluster, basically data should be replicated, as we discussed, in a synchronous manner, right? There's always going to be strong consistency when you're replicating data. It's not eventually consistent, which is kind of the hallmark characteristic of NoSQL, which isn't bad because for some workloads and for some use cases, that's perfectly acceptable. But we do want to make a sharp distinction between distributed SQL systems are always going to have strong consistency in regards to replication, whereas NoSQL systems are going to replicate the data internally in an eventually consistent manner. I won't get into lightweight transactions and all that stuff. It gets a bit nebulous real quick. Here we're talking about out-of-the-box core characteristics of these systems. Distributed query execution, yeah, obviously, right? If you have a distributed system, the expectation is that it can handle a query where your data is laid out across a various number of nodes. Distributed ACID transactions, of course, that's going to be a hallmark of distributed SQL. NoSQL, not so much. Again, I'm not going to get into a conversation about lightweight transactions and their quorums and all that good stuff. Let's just talk about the fundamental core characteristics of the systems. NoSQL is not going to offer those kind of rollback save points and all that stuff that you're going to expect in a distributed ACID transaction. So that's the core differences between a distributed SQL system and a NoSQL system at a high level. Generically, I should say. Okay, so that tells us what distributed SQL is. It kind of tells us the difference between distributed SQL and a NoSQL system. So really, what's the difference between a monolithic database, a SQL database, and a distributed database, right? So here on the monolithic side, we can think about things like Oracle, SQL Server, DB2, Postgres, MySQL, all your classic databases, right? And the prevailing idea, as being an old MySQL guy, that when you want to get more capacity, right, you want to serve more clients, get a bigger workload in play, the general idea is before you start doing anything crazy, just throw more hardware at the problem, right? Just get to a bigger box, right? More CPU, more RAM, more storage. You basically scale up, right, to get more capacity. The converse is true with distributed databases, and kind of NoSQL are the ones that kind of started this, but now with distributed SQL, the idea stays the same, which is that you want to be able to simply add more nodes to get more capacity, right? And the system should be intelligent enough to kind of rebalance and should give you more read and write performance as a result. I'm not going to dismiss the fact that you can take a monolithic system like, say, MySQL, and then you can start thinking about, well, I'm going to shard my data so that some writes go over here and some writes go over here, and then I'm going to attach read replicas to these other things, and God forbid the replication breaks, and now I have to sync the whole thing, and as an application developer, I got to know where the data is. Yeah, we've been talking about that and doing that for the last 25 years. It's not a pretty thing, right? That the appropriate way or the proper, cleaner way to solve that problem is with distributed SQL. So you operationally don't have to set any of that stuff up or manage it in the event of a failure. Third or second, as a developer, I don't need to know about any of that stuff. I just do my select, I do my insert, I do my update. The behavior that I expect just happens regardless of the fact that the data may be replicated n number of times behind the scenes. Again, the recap here is monolithic databases. Generally, if you want more capacity, you scale up, you throw more hardware at the problem. If you want to get more capacity in a distributed database, the idea is simply add more nodes to get more capacity. You basically scale out. Okay. How do distributed databases scale out? Touched on this just a little bit briefly. Look, the prevailing way that these things happen is that data is sharded, right? Is that in a nutshell, I guess a real simplistic way to think about it is if you have a table of data, you're going to divide that table up and spread it across multiple nodes, right? So in the graphic, right, on the right-hand side, you probably see what the problem here is, which is that, okay, that's great. You've sharded my table, right? And you've spread it out across multiple nodes, which is great. But what happens in the event of a failure? Like if I lose my first node, I kind of lose part of my table, and that's not awesome. Yeah, we'll get to that in just a second. But the idea here is how can we achieve more scale? You shard your data, you spread it out across multiple nodes, and then of course, you're going to need to replicate it. We'll get to that in just a second. Okay, so let's recap. What's the difference between a distributed SQL system and a monolithic database like Oracle or Postgres or SQL Server? Again, we're going to walk through the same characteristics. SQL API, of course, that's what they both are. Distributed data storage in a distributed SQL system, the expectation is that 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 data is going to be distributed automatically. You don't have to think about it. You can do it, I guess, in a monolithic system, but it's not a cluster. So really what you're doing is you're setting up read replicas and write shards, and you're creating a bunch of complexity. There's nothing out of the box if I install Postgres that gives me that immediately. There's nothing out of the box if I install MySQL that gives me distributed storage immediately. I either have to use somebody else's software, I have to use my software, or I have to do other things like that. All right, replication. Here we want to be very sharp about what we mean about replication. In a distributed SQL cluster, it's a cluster, we have nodes inside of the cluster, and that replication is going to be synchronously replicated, right? So the data inside of a cluster is synchronously replicated. That concept does not exist in a monolithic RDBMS, right? I'm not going to get into read replica architectures and all that stuff. The only way that you can kind of replicate from one system to another, whether it be MySQL or Postgres or something like that, is asynchronously, right? So if you're reading from a read replica, you have to have the expectation that the data may or may not be current, right? Because there's going to be some lag in the time that it takes to replicate that data. So we want to be really sharp about what we mean when we talk about replication. Replication in a distributed SQL system, we're talking about the replication that happens internally inside of the cluster. That data is being synchronously replicated, so there's a consistent view of the data at all times. In a monolithic system, that concept doesn't exist because it's not a cluster, right? You can asynchronously replicate to other nodes, other read replicas, but the replication works at two different levels when we're talking about these two different systems. Hopefully that's clear. Don't worry about it. We're gonna drive home this point in subsequent slides. Distributed query execution, that comes out of the box inside of distributed SQL. In a monolithic system, yeah, I guess you could use your software or somebody else's software. You can wire it all up to make it work, but it's a lot easier to just use distributed SQL to make that happen. Distributed ACID transactions, out of the box, that's a thing that you're going to expect is just going to automatically happen, where you do not have to think about it. There's no extra software or logic that you need to build to make that happen. Distributed ACID transactions are just something that comes with the kit. Whereas in a monolithic system, yeah, there's extensions and other software and other wacky things that you can do, but it isn't anything that anybody's going to do right out of the gate. If anything, people are going to try and avoid that at all costs, and that's why distributed SQL presents such an interesting alternative for people that are looking at monolithic systems or using monolithic systems today and thinking about, how can I get distributed query execution? How can I get synchronous replication? How can I get automated data storage? And how can I get distributed ACID transactions and still interface with the data in a SQL API, right? That's where distributed SQL starts to get really, really interesting. All right, so given the context of what distributed SQL is, how that's different than a NoSQL system, and how that differs from a monolithic system, let's put Yugabyte in that context. And the soundbite here is that Yugabyte is an open source, and here we want to remember that Yugabyte, the entire database, there isn't some features that are open source and some that are not. The entire database is Apache 2.0 license. Backups, security features, the whole deal. The whole thing from beginning to end is open source, Apache 2.0 license. So Yugabyte is an open source, high performance, distributed SQL database. So here we're clearly saying that Yugabyte has all those 5 characteristics that we talked about that we would expect from a distributed SQL database. It's built on a scalable and fault-tolerant design that's been inspired by Google Spanner. And we'll get to, in just a second, answering the question, well, how much is it like Google Spanner? Is it the same thing? Is it different? How does it differ? But just remember that the design, right, or the genesis or the idea for Yugabyte all came from Google Spanner. It's a direct inspiration from that. Yugabyte is Postgres wire compatible, in this case 11.2, and we'll dive deep on how we achieve Postgres compatibility, but that's our aim here, is to provide a Postgres wire compatible distributed SQL database that's cloud native and supports advanced RDBMS features like stored procedures, triggers, and UDFs, right? Because if I told you, hey, here's a SQL database, but you can't do stored procedures, you can't do triggers, you can't do UDFs, you can't do secondary, like, then you start thinking, well, that's not really a SQL database, right? It's something that's kind of like a SQL database, but it's not really. And that's really the expectation that you should have of these systems, is that it should look, smell, and feel like you're interacting with Postgres or MySQL or some sort of monolithic system that you're used to, and all that kind of magic happens behind the scenes, right? That's really the goal. Okay, so I preface this a little bit, which is Yugabyte is directly inspired from Google Spanner. So of course the question is it the same? Is it different? So let's run through these characteristics on the left-hand side. SQL API, of course, Yugabyte is going to strive for Postgres compatibility. Google Spanner is, depending on what you're trying to do, inserts, updates, selects, DDL, it really kind of depends what action you're trying to do, where you may have a SQL interface, you may not have a SQL interface, you might have some proprietary language that you have to use to make that happen. So we can arguably say it doesn't have a SQL API. It has something that tries to be that, but it's not. You can't take your MySQL or your Postgres skills and in the first day be jamming on all kinds of Google Spanner stuff. You just won't. The language is not there. Whereas conversely with Yugabyte, our expectation is that in this case, if you know Postgres, on day one, you're ready to go. You should be able to start interacting with the database. And I'll kind of show that in our exercises. Distributed data storage, of course, they're both automatic. Replication inside of the cluster, they both do it synchronously. Support for distributed queries and ACID transactions, of course, both systems are going to support that. Yugabyte is open source, as I mentioned, Apache 2.0 license. Google Spanner is a service, right? It's not anything you can download, run locally, run on somebody else's cloud. It's a service, right? So open source really isn't a thing in Google Spanner. So if you're looking for software that you can arguably control, manipulate, and open source matters to you or your company, Yugabyte is definitely a strong choice in this particular regard. Consensus algorithm. And we'll double click on how consensus algorithms work inside of a distributed SQL system. But for argument's sake, Google Spanner uses a consensus algorithm called Paxos, while Yugabyte, along with dozens of other distributed projects and databases, use Raft. It's super popular consensus algorithm. And in a pedestrian way, Raft is merely a much easier to understand version of Paxos. And then on the networking side, Yugabyte is kind of going to be at the mercy of wherever you install it, right? So if you install it on AWS, right, that's your networking layer. If you install it on Azure or Google or in your private network, in your own data center, if you have a crappy network, you have a crappy network, right? All distributed systems are not going to function particularly well if it's slow, if it's insecure, if it's unstable, right? That's kind of the nature of the beast with distributed systems, is that there's RPCs, right? That's the trade-off that you make. So a bad network is going to mean a bad distributed system experience. It's whatever the networking is that you bring to the table, your cloud provider or your private data center. And we use hybrid clocks, right, which a lot of other projects use as well. Google Spanner is obviously going to be running on Google's proprietary network, and it's going to use atomic clocks. I guess as a final kind of characteristic here, which may or may not matter, I guess it all depends on what your budget is, but Google Spanner, if you've looked at it, is obviously incredibly expensive. It's really out of reach for developers, enthusiasts, small early stage startups, even mid-market companies. If you've looked at what it costs to do a production workload on Spanner, it's prohibitively expensive, right? So if your use case merits it and you got to have all those bells and whistles and you got to have the Google name, yeah, I guess it makes sense, but there's very clearly other alternatives that are going to be much more cost effective, open source, and be a lot more friendly from a pricing standpoint at that regards. But I'll let you explore that particular piece on your own. Okay, so next up, CAP theorem. So if you've been kicking around databases or even distributed systems, you've probably heard about the CAP theorem. And in a nutshell, here's your soundbite. In the face of a network partition, it's possible to solve for either consistency or availability, but not both. What does that mean? So let's take some practical examples. For example, Cassandra. Cassandra would be considered an AP database, meaning that it puts a premium on availability if it encounters a network partition. So it's more important that clients be able to access data, even if it is incorrect, right? Your workload or your use case may allow for that, right? It's not a big deal, and that's cool. You're putting a premium on availability. over the consistency or the accuracy of the data. Whereas with CP databases, of which Google Spanner and Yugabyte are, here we're putting a premium on consistency in the face of a partition, a network partition. And what we mean by that is that in the most extreme example, right, the most extreme scenario, both systems will shut down, the databases will shut down if they are unable to provide a consistent view of the database, right? That consistency of the data, like systems of records and things like that, that is put at a premium over the availability of the system, right? So that's the CAP theorem, and that's kind of its thesis, is that, again, in the face of a network partition, you can only solve for either consistency or availability. The thing to want to walk away with is that Yugabyte in this scenario would be considered a CP database, much like Google Spanner is. Quick question from Mike J. Are there plans to go from PG 11.2 to 12? Yes, in the future we will be rebasing. I don't have a timeline for that, but yes, the idea is to be rebasing. And later on, you'll actually see how we're reusing Postgres code base, and it'll probably come a little bit clearer on how potentially rebases work. Okay, Raft consensus algorithm. I talked about this earlier. Raft is a consensus algorithm that's essentially an easy to understand version of Paxos, because it kind of breaks down a lot of the problems that Paxos aims to solve. The only thing that you really need to know here is that Google Spanner uses Paxos, and tons of projects that are, distributed projects that need some sort of consensus algorithm. Overwhelmingly, I think Raft is one of the most popular ones that they all use. So we're not alone here as far as adopting Raft as a consensus algorithm. And then the final piece that you want to remember from here is that Yugabyte uses Raft to achieve consensus between leaders and followers in a tablet peer group. All right, so there's some kind of new concepts that I'm throwing at you here. Don't worry, we're going to double click on all of these. But all you got to walk away with here is that Yugabyte uses a consensus algorithm. Why does it use it? It uses it to drive consensus between leaders and followers, right, in a tablet peer group. What's a tablet peer group? Well, remember that when we distribute data inside of the system, it's not enough just to distribute it. We want to have more than one copy of that data, right? So if you have more than one copy of that data, let's say we have 3 copies with a replication factor of 3, we want to have one leader, right, of those 3 pieces of data, so that that leader can basically say, I have the right, who else has the right, you have the right, perfect, let's commit it, right? You need some leader of that shard, of that particular tablet or shard, to make that decision, right? And you have to drive that consensus using some mechanism, and that mechanism is going to be Raft. Don't worry, we're going to double click on this particular topic later in the presentation, but that's the takeaway that you want to have with Raft. It's a consensus algorithm, and Yugabyte uses it to drive consensus between its leaders and its followers. Okay, third section, YugabyteDB Architecture. And here's where we're going to get a little bit in the weeds, but we'll slowly ease our way in, and hopefully it all makes sense. Okay, let's start with what are the main components, right, that comprise a YugabyteDB cluster. At a base level, there's nodes, right? Nodes can be machines, they can be VMs, they can be containers. It's whatever vessel, right, that you want to run your node in. Sky's the limit here on kind of how you want to do it, bare metal all the way to Kubernetes. A universe, or a cluster, right, is merely a group of these nodes that collectively function as a clustered database, right? So you have to have 3 nodes at a minimum, but it's 3 nodes, it's 27 nodes, it's however many nodes it is. But if they're all logically grouped, right, to form a Yugabyte cluster, that's the cluster. It's all those nodes that are synchronously replicating data. You can have a primary cluster and optional read replicas, right? So if we look at this graphic here, okay, that's a YugabyteDB cluster. But much like monolithic systems, where in some circumstances you want to bolt on a read replica, right? You accept the fact that I'm asynchronously replicating, but maybe I want to create a reporting database where it's fine if there's a 5-minute delay between the data. Or, hey, I just want to do a backup, have a standby database. Or, hey, I just want to bring data that I don't care might be a little bit stale. I want to bring it closer to a user who might be in a far off geographic location, right? So Yugabyte does also support that setup, right, that you would traditionally do with something like MySQL or with with Postgres, right? So you are able to do that. So you would have a Yugabyte cluster, and then you would asynchronously replicate to some other cluster for whatever reason in whatever place that you wanted to. So the takeaway here that you want to remember is you've got nodes, and they can be on everything from bare metal to containers. These nodes are grouped together to form a universe or a cluster, right? It's an interchangeable word there. A cluster has to have at least 3 nodes, and you can optionally bolt on some read replicas, and that replication is going to be asynchronous. While if we recall that within the cluster, right, we're going to be replicating data synchronously. So we're always going to have a consistent view of the data whenever we talk to the cluster. All right, let's go one level deeper here now and kind of look at what the core pieces of the architecture, core pieces of the stack are going to be. So at the top layer, right, we have the thing that as a client or as a tool or an application or as a developer, how am I going to interact with the database? And we already talked a little bit about SQL API. There's also a Cassandra styled API as well. So you have those 2 different flavors of depending on how you want to model your data access patterns, whether or not you need referential integrity. We do offer those 2 modes of interacting with data inside of Yugabyte, a YSQL API and a YSQL API. And we'll double click on these in just a second. But just understand that there is a top layer, right, that we interface with, and that's the query layer. Below that is obviously going to be our storage layer, right? So this is where basically data gets stored, it gets replicated. There has to be some sharding and some load balancing. We have to manage distributed transactions, right? There has to be consensus about when it's okay to write data, who's the leader of the shard. All that happens in this kind of lavender slice of this graphic. And we'll double click on each one of these pieces. So the only takeaway that you need to have here is that there's basically 2 layers inside of Yugabyte in the stack. There's a query layer, and there's basically a data storage layer underneath. Okay, one more double click, and that's going to be on services. So if I'm running Yugabyte, what are the services that I want to look out for? Essentially, there's 2 processes, right? There's going to be a T-server process, and this is the process that hosts and serves data. And then there's going to be a YB master service, and that's what's going to store metadata for the system. So things like, hey, I want to do a backup, or hey, I want to create a table. Where's that shard? Who's the leader, right? Think of it as kind of all that administrative metadata, right, about the cluster itself. And that's just a quickie screenshot from a local 3-node install. But those are the 2 services, right? And that's the function that they provide to the cluster. T-server hosts and serves data. YB master stores metadata for the system. And we'll double click on each one of these for a deeper dive. T-server service, again, it hosts and serves user data. And at a high level, we want to think that tables are split into what we call tablets. Just think of tablets as shards. It's kind of an easy way to think about it. We just use the term tablet. And that's the typical way that a distributed database is going to achieve a degree of scale, right? Or the ability to add nodes to get more capacity is the first thing to do is we have to shard the data, and we have to do that in an intelligent way. Again, the thing to remember is that just because you shard the data, that's not enough. You have to actually replicate it as well. Otherwise, if you lose a node and you lose the shard and it isn't replicated, your database is effectively down, right? You can't reconstitute that table. So the T-server service is the one that kind of manages that piece, right? And you can see from the graphic, granted it's overly simplistic, but the point here is that we're just trying to convey an idea where we've taken a table and we've sharded it into 3 different tablets, right, or 3 different shards, and then we've distributed those shards across our cluster, which is comprised of 3 nodes. In this case, it has a replication factor of 3, right, because you can see we have 3 copies of every single tablet, and then each one of those tablets has a leader, and the leader is what's going to be able to say, hey, I got the right, who else has the right? You got the right, fantastic, let's go ahead and commit that. Or let's say we lose a node, we lose node 1. In that event, node 2 or node 3, tablet 1, one of those followers needs to become the leader. And that's where the Raft consensus algorithm comes into play. T-server service, that's what hosts and serves data, basically does all that data management that we would expect. The other service that we talked about, which is the YB master service, That's going to manage your system data metadata, or manage your system metadata, as I talked about. So this is information about tables and tablets and nodes and the cluster, things like any sort of manipulation to the DDL, who are the leaders, who are the followers, what's the node count, load balancing, backups, restores, adding nodes, removing nodes, right? All of those kind of operations are going to be tasks that are going to be handled by the master service. All right, let's go back into our graphic, and in the red box, this is the piece that I want to focus on for this particular slide, which is going to be the data storage layer. DocDB, what is that? Easiest way to think about it is it's our storage engine, right? It's not another database. It's not a product from Microsoft. It's merely us using RocksDB as a starting point, forking it, making it distributed, and adding all these enhancements to it so that we could then have a distributed data store, right? That's kind of the foundation of what this lavender slice is. So what is the soundbite? DocDB is Yugabyte's distributed document store. Think of it as its storage engine, responsible for transactions, sharding, replication, and persistence with roots in RocksDB, right? It's transparent to the end user or you as an administrator. This is merely to kind of help you understand what is actually going on inside of the system and how does it all come together. And as I mentioned, within this layer, right, this data storage layer in which DocDB is the storage engine, we want to make sure that we have strong write consistency, we're resistant to failures, that sharding and load balance happens automatically. I, as a developer and administrator, do not have to think about this, and that the system is aware that data may be in different zones or regions or even different clouds, right? We have some customers that do that. And I also have the option of tunable read consistency. DocDB, it's our storage engine. It has roots in RocksDB. Those are the types of features and functionality that this layer is going to provide to the cluster. Let's rewind a little bit and think about, okay, you mentioned how data is sharded, right? So here let's do two slides that just kind of help drive home the point about how we shard data. And remember that sharding data is how you get scale in distributed databases. So simplistically, tables are sharded into tablets by rows, right? Think of tablets as shards. Those words should probably be interchangeable. So a row's primary key is what's going to determine the tablet that owns it, right? As well as the node that it resides in, right? And it's pretty simple, right? What we're showing here in this graphic is we have this table and then we shard it and then we move certain rows into certain tablets, right? And then if you want to extend this out, you can remember that these tablets are then placed on nodes, which are then replicated synchronously across n number of nodes, depending on your replication factor. So Yugabyte's going to support two sharding strategies, right? You can either do it on a hash or you can do it by range. I believe hash is the default, and that's what we go with. So let's do kind of a more zoomed in view on how this sharding actually works. Is every row essentially is a document with a primary key, because you want to remember that foundationally we're using our storage engine DocDB, which is a document data store. So a primary key is going to consist of one or more hash components and zero or more ordering components. You can kind of see on the right-hand side on the graphic, kind of a simple explanation of kind of how that all comes together. And these keys are going to help determine the row's uniqueness and its shard location. So that's how the sharding works internally inside of Yugabyte. Again, this is all transparent to you as an administrator or as a developer, unless you actually want to go in and say, for example, you want to use range partitioning instead of the hash partitioning. Okay, replicating data. Okay, we've been kind of driving home this point, is that Yugabyte's replication, its design, right, internally, how it keeps a consistent view of the data. It's inspired by Google Spanner. We talked about how tablet peers form a Raft group. Again, tablet peers are going to be shards that are identical, that have the identical set of data. And we want to make sure that that data is synchronously replicated. There has to be a leader of that particular shard that can acknowledge when a write is, coordinate the other writes, understand when it's time to commit. If it goes offline, followers need to figure out, okay, who's the new leader etc. And these tablets can, of course, span nodes, zones, racks, regions, right? Because you may have a node in one environment and another node in the cluster on a completely different environment, and tablets need to be aware of that. They may not be sitting on the same infrastructure. And as I mentioned, writes are logged by the majority of peers and then are applied to storage. So there has to be some consensus that, yes, we have enough copies of the data. Yes, now we can actually commit it and apply it to storage. Let's move up a layer. And now let's focus on the query layer. So the query layer, what we really want to walk away with here that I kind of prefaced already is two things, right? Query layer is going to do everything we expect a query layer to do. But there's essentially two APIs that you can leverage to communicate with the cluster, to develop against it, to get data in and out, manipulate it, update it, to create objects, etc. There's a YSQL API, which is Postgres compatible, and that's going to be obviously the best for relational workloads. Basically, if it's not a good fit for Postgres, it's probably not a good fit for YSQL. The other API that you have at your disposal is going to be YCQL, and this is going to be a Cassandra-inspired API for semi-relational workloads, right? So you don't need foreign keys. You don't want to think about data models. You're all about performance. It's quick key value lookups, right? If that's what your data set looks like or what your use case looks like, YCQL might be something to think about. Yugabyte gives you both of those options as far as how you want to develop your application. Now, how can I interface with this query layer, right? You can obviously do that at the command line using the shell, but there's also, you can use third-party tools, and I'll show you how to do that later on in the presentation. Or if you want to use tools like Airflow or other things like that, Java, Python, Node, Go, all the typical drivers that you would typically use with Postgres are going to be able to connect to Yugabyte. And we'll double click on what exactly we mean by Postgres compatibility and how that's achieved. But net, right, you can interface with these APIs either using the command line, a third-party development tool, or using JDBC or any of the drivers that you want to use. Okay, let's double click on one of the APIs. In this case, let's double click on YSQL. And we'll show a bunch of exercises in YSQL during the exercises section. And YSQL is a Postgres compatible API for relational workloads, as I mentioned. It's going to be best for RDBMS styled applications, system of records, things like that. Supports foreign keys, joins, distributed transactions, partial indexes, triggered sort procedures, everything you expect, and some Postgres extensions. So if you're coming from the Postgres world, you know that there's a bunch of extensions that you can bolt on to a base Postgres installation to do search and indexing and get all these other things. A lot of extensions work with Yugabyte, some don't. And the ones that don't specifically interface in a very intimate way with the data storage, right? So if the extension can't understand or work with distributed data storage, then it's not going to work out of the box. So we're slowly working through the extensions to extend them so that they can work with distributed data storage, because these extensions were designed for monolithic systems. They were not designed for distributed systems. So there's some work on some extensions that needs to happen, but some work, like the cryptographic ones and things like that, work. As I mentioned, it's compatible with Postgres 11.2. Rebasing, of course, will happen in the future. Okay, YCQL. With YCQL, we're getting some feedback on your mic. Are we still getting feedback on my mic? Maybe, I don't know. I'm going to continue on. So YCQL. So with YCQL, that's again going to be a Cassandra-inspired API for semi-relational workloads. So if you've got an OLTP-styled application or an HTAP-styled application where it's all about massive data ingestion and you're just doing quick key lookups, YCQL may definitely be something that you may want to check out. It does support, so it's going to be a little bit different is that, like say, for example, if you're coming from the Cassandra world, is that there is support with our CQL API for strongly consistent secondary indexes, a native JSON type, and distributed transactions, right? Out of the box, not lightweight transactions, like real deal distributed transactions, if that's functionality that you're going to need. So it's some definite pluses if you're coming from the Cassandra world and, hey, I wish it did this. I wish it had secondary indexes, or I wish it had a native JSON type. YCQL might be something worth investigating. Okay, let's drive home another point, and this is going to be around node counts, replication factors, as well as fault tolerance. So fault tolerance, or FT, is the maximum number of node failures that a cluster can survive while still preserving the correctness of data, right? So at what point does this extreme scenario happen where essentially the cluster will go offline? Because we want to remember that we are putting a premium on consistency versus availability, right? As a system of record, you obviously do not want to jeopardize the data in any way because obviously it's very problematic. In a system where it's like you don't really care about the data, yeah, just keep the thing available. If there's some incorrect data, that's okay. In this scenario, we don't, right? So how do I determine the right number of nodes, or how do I determine what my replication factor needs to be in order to survive a certain amount of node failure? So we want to remember that Yugabyte replicates data across nodes. This is how it achieves its availability mechanism, like all distributed databases do this. The replication factor, or the RF, is the number of copies of data in the cluster. So let's walk through a scenario. In order to achieve a fault tolerance of a certain amount of nodes, the cluster has to be configured with, and this is the formula that we use, replication factor equals 2 times the number of nodes that can fail plus 1. So in the graphic, we kind of have a simplified example, which is that in order to survive the failure of one node, you need an RF factor of 3, right? So 2 times, I want to be able to survive the failure of one node. So 2 times 1 gives me 2, plus 1 equals 3, which means RF factor of 3, right? And we'll demonstrate live during our, our high availability fault tolerance demo exercise. We'll see how this actually works. But at the end of the day, that's the formula you need to remember. Replication factor equals 2 times the fault tolerance, meaning the number of nodes that you're willing to lose and still have a consistent data set, plus 1. And don't worry, this is all in the exam prep materials, but it's just the general concept that you need to wrap your head around, that there is a bit of a method to the madness in regards to what should be the appropriate replication factor that I need for my cluster. Okay, let's zoom up and think about, okay, given all that, given the processes, the different layers, how data is replicated, appropriate replication factor, what are my options as far as deployment configurations? And I already touched a little bit on this one, but let's recall that data in a cluster is replicated synchronously between nodes. All nodes can be in a single zone. Nodes can be in multiple zones. Nodes can be in multiple regions that are geographically replicated. Nodes can even be in multiple clouds, both public and private. They can be VMs, they can be containers, they can be bare metal, right? And you want to recall that after you've set up your cluster, right, which is synchronously replicating data internally, you have the option of bolting on additional clusters, right, and asynchronously replicating to them, like you would traditionally with a MySQL or a Postgres styled system. So let's get a quick visual. Again, on the left-hand side, this is what our 3-node cluster looks like. Synchronous replication between the nodes. We have our tablets, our peers, our shards, all that good stuff. And on the right-hand side, of course, hey, I want to bolt on another cluster. I can asynchronously replicate between the clusters. That's all. I know I've been kind of driving this point home, but it's really important to understand that asynchronous replication is the province of monolithic database to monolithic database, or the replication that happens internally inside of a NoSQL system that is eventually consistent, which is a sharp demarcation from how distributed SQL systems replicate data, which is always synchronously between nodes, so that there is always a consistent view of the database. Okay, let's go to, I've got my deployment. We talked about the CAP theorem. Let's talk about network partitions, right? So this isn't going to be unique to Yugabyte. This is like a classic problem, is what happens in a network partition. Well, when a network partition occurs, essentially what you have is that you have clients that can talk to either side of, or that can talk to either side of a cluster, right, that has been partitioned in some way by the network, right? So in the graphic, albeit a little bit simplistic, is that on the left-hand side, you have a node that can no longer communicate with the other members or the other nodes in the cluster, whereas the 3 nodes on the right are communicating fine with each other. You can see what kind of problem emerges here, where if clients are able to talk to either side of the cluster, I can start doing updates on the left-hand side. I can be updating the same rows on the right-hand side. And the longer that this goes on, the further that these systems are going to start drifting, or I should say these partitions are going to start to drift apart. And as they drift apart, you can imagine the calamity that ensues when these nodes start talking again, because they are going to have a highly inconsistent view of the data, and it turns into a big mess, right? So the question is, how do we solve for this problem, right? And because Yugabyte, like Google Spanner, is a CP database, this is how we kind of tackle this problem. So in the face of that network partition that we just showed, what would happen is that node 1 would essentially go offline. Why? Because prior to it going offline, it knew that, hey, I'm a member of a cluster that has 4 nodes in it. And if I can't communicate to the majority of the nodes, it means I'm the odd node out, which means I should not be serving any reads and I should not be serving any writes. That way, if a client tries to communicate with node 1, it will not be able to. It will be forced to have to communicate to either node 2, 3, or 4. Why is that okay? Because node 2, 3, and 4 can still provide for a consistent view of the database. You can see that all the shards are resident within those nodes, so I can reconstitute the entire database. I also am able to keep multiple copies of the database, so I have leaders and I have followers. I've essentially gone from a 4-node cluster to a 3-node cluster, despite having a network partition, but my system is still up. It is still available. So this architectural design is very similar to Google Spanner, which again is also a CP database. Again, here we're trying to drive home the point around the CAP theorem, which states that you can really only solve for 2 problems in regards to a network partition: availability or consistency. Okay, quick word on secondary indexes. All you need to know here is that Yugabyte supports strongly consistent secondary indexes. Why is this valuable? Well, you want a secondary index if you want to do fast lookups on columns other than the primary key. It's also a mechanism for being able to enforce the uniqueness of column values. Those are really the 2 takeaways that you want to have here around secondary indexes. And yes, these are reiterated in the exam prep guide. Okay, so now I want to close up this section with 2 kind of advanced topics. These are 2 capabilities that are inside of Yugabyte that you won't find necessarily in other systems, or they might be new concepts to a few of you in the training. Co-located tables. What is a co-located table? Let's say we have a scenario where we have lots of tables, lots and lots and lots of tables, but they actually don't have a lot of data inside of them. And what we want to avoid is having lots and lots of shards, right? Lots of tables, not a lot of data in them, but tons of shards, right? It just it creates a lot of unnecessary overhead. So one strategy that you can do here is, and this is a intervention that you can have, is let's take all these small tables, right, that don't have a lot of data, for example, and let's put them all into a single tablet. What's the advantage of that? Well, the advantage of that is that let's just say I have a query that has to touch table A, B, and C. I just avoided a ton of RPCs, right? Because the tables are small, they don't have a lot of data, and if they're all co-located in the same shard or tablet, I'm going to have a way more efficient way of being able to access and manipulate that data. And I can actually, because I have less tablets, it means I essentially have less metadata that I need to deal with. The other upside here is going to be that remember that even though I've co-located all of these tables into a single tablet, tablets are still replicated, right? So it doesn't mean that, hey, I don't have as much availability or resilience with my tables because I've co-located them. You have the same amount, right? Because just because you've consolidated tables into a tablet, into a co-located tablet, doesn't mean you lose out on that. Those tablets are still going to be replicated out. And that's really all you need to know here, is that co-located tables are a way of being able to consolidate tables into a single tablet, which are still synchronously replicated. The last advanced feature or piece to think about that's resident inside of Yugabyte is change data capture, right? And that's probably a pretty familiar concept for some of you. So internally inside of Yugabyte, and this is optional functionality that you can leverage, open source, of course, is that let's just say that you've got Yugabyte, it's your system of record, and you're constantly making changes. And let's just say that, hey, I want to stream those changes out, and maybe I want to stream them to Kafka. I want to put them into a reporting database. I want to log them for auditing purposes. You can set that mechanism up and start capturing these changes and then streaming them out to other systems, right? Whether it be a logging mechanism, whether it be to another database, whether it be to something like Kafka, which in turn sends it out to other things. Change data capture, that's all you need to know. Okay, this is the final section before we jump into our exercises, YSQL API. Okay, let's think about the YSQL API and how we're able to achieve a high degree of Postgres compatibility. So in this graphic, granted it's a little bit crude, but if you're coming from the Postgres world or even from other databases, you can see these components are pretty familiar, right? Because this is how Postgres works, right? In the green box is basically its query layer. And then down below, it's got the mechanisms that on how it writes data to disk, right? Pretty standard, pretty basic, monolithic. This is how Postgres works. These are the key components. A lot of other systems kind of have very similar architecture. So the thing that you want to take from this slide is that this is Postgres's architecture, and what we did with the green box that's highlighted here, Yugabyte reuses that. It basically takes the Postgres code and puts it into Yugabyte, right? So we don't reinvent the wheel. We don't have to re-implement how stored procedures work or how user creation works or how triggers work, right? We are essentially taking that code and putting it into Yugabyte, which gives you a massive advantage as far as getting onto the road to having a fully Postgres compatible database. So we lift and shift. We reuse the Postgres query layer. So then you think, okay, great, you're reusing the layer, but you can't have single disk storage underneath. You have to take advantage of this DocDB thing, right? Yeah, so that's the point, is that we replace those mechanisms that Postgres has with the distributed data storage layer, right? Remember that DocDB storage layer? That's what now this query layer is interfacing with. So at this point in the graphic, we have Postgres query layer, and then we have this DocDB storage engine, Yugabyte distributed data storage underneath. We wish it was that easy, right? You need to make things like the planner, the executor, and the optimizer. You have to enhance them, optimize them, change them so that they're aware that data isn't on a single disk, right? That data is in fact in multiple locations, right? So if you're gonna do query planning and optimization, you have to take into account that data is not located in the same location. Data may be located in very many different locations. So those are optimizations and modifications that we need to make or have made to Postgres's query layer to take advantage of that fact. And that's really the work, right? That's the work, right? When we talk about, hey, that feature is not yet supported, this is the reason why, right? It's because that particular feature needs to become aware that data is not in the same location, that in fact it is in different locations. We have to make it distribution aware, so to speak. But that in a nutshell, right, is how Postgres's query layer, Yugabyte's DocDB storage engine, they come together, right, to give you this Postgres compatible distributed SQL system. What does that mean? Like, what's the advantage that you get from that? And the advantage that you get from that is that you essentially get a stateless Postgres, right? And we'll demonstrate that during our fault tolerance exercises, which means that as a client, I can connect to any node, right? Any YSQL, any node running the TServer service, right? That's our query interface. And I just gotta, if I lose my connection, I just connect to another one, right? I don't lose the whole system just because that query layer goes offline. And it's a stateless tier, right? This is the best way to think about it, is that hey, if I lose my connection or that node goes offline, I just reconnect to another node and I still have a consistent view of the system. So it's self-healing against failures. ACID compliance, I won't belabor the point here, but as I mentioned, Yugabyte is going to support distributed ACID transactions. What's the two takeaways here? Two takeaways are that YSQL supports two types of isolation when we're talking about transactions: snapshot isolation, also known as repeatable read, and serializable isolation. So you have those options in how you want to set your isolation level. And YSQL, which is the Cassandra compatible API, that's going to support snapshot or repeatable read isolation. Those are the options that you have depending on the API that you want to use. Now, I'm just going to give you a sample of some of the Postgres compatibility features, right? And you can see, I mean, we're not going to run through each one of these, but really the takeaway here is that a lot is supported, right? And again, the idea was that if I know SQL, like ANSI compliant SQL, and I'm moving from one system, MySQL, Oracle, SQL Server, whatever, I should be able to take a lot of that skill and knowledge that I already have about working with SQL and take that right into a distributed SQL system, right? So all this sort of functionality out of the box, again, because we're reusing that query layer, is going to give you a real head start as a developer. I do want to call out two things, which I probably mentioned already. One is the alter. As you can imagine, doing an online alter operation is challenging enough in a monolithic system, but in a distributed system is even more challenging. So there are some caveats. There are some alter operations that are not yet online, but a variety of alter operations like adding columns and things like that are supported. Extensions, as I mentioned, if the extension doesn't do any heavy lifting with the data storage layer, like cryptographic type of extensions, they're going to work out of the box. But it's those extensions that require indexing or some intimate interaction with the data layer. Those we have to go in and we actually have to enhance those extensions so that they can understand distributed data storage, much in the same way that we have to retrofit the query layer, the Postgres query layer, to understand that you're dealing with distributed data. You're not dealing with monolithic data that's all in one place. And again, this is just to give you an idea for the sort of functionality, clauses, expressions, etc., that are supported inside of Yugabyte. Okay, let's jump into some exercises. Now, if you haven't already done so, not a big deal, because it's super straightforward, is if you want to do quick and dirty, up and running, I just want to get to a YSQL shell, you can do this on Linux or Kubernetes or other things. I'm just doing Mac here, but the instructions are pretty much the same. You want to basically download Yugabyte. You want to unzip it, navigate to the install directory, and run the YugabyteD start command. That will get you a single node, YugabyteDB. It's not technically a cluster because you only got one node, but look, if you just want to be quick and dirty and you just want to get to a YSQL prompt, this is the fastest way to get started. If you want to be mildly more sophisticated and you want to do a 3-node cluster, right, which is running locally on your laptop, just to kind of get the look and feel, the interaction with different nodes and processes, it's exactly the same. Download the software, unzip it, move into that directory. And then what you see here, what I'm doing with my command is that I'm specifying RF3. And that's replication factor of 3. That means by default, it's going to create 3 nodes. And we'll walk through this installation so you see kind of how it all works. And then if you want to connect to YSQL, assuming that you're in the directory, just call in the bin directory the YSQL utility, and you're at a command prompt. This is literally all it takes to get to that, to get to the SQL interface. And from here, you can start building databases, creating users, assigning them passwords, selecting data, all that good stuff. And I'll walk you through all of this. You can also, equally as easy, and this is why I mention it, you can do a 3-node installation on Google Kubernetes, on GKE, I should say, just as easily. It actually doesn't take that much more time. I mean, granted, GKE is not as fast as your local laptop, but it probably takes another minute or 2 tops to get up and running with Yugabyte, a 3-node cluster in GKE. It's super straightforward, right? So if you've worked with Helm before, or even AKS or EKS, you basically add Yugabyte, right? You add the Yugabyte chart, you update it, make sure you have the current version, you validate it. I guess that's slightly optional. You create your namespace. In this case, we're creating a namespace called YB demo, and then it's an install, right? You install Yugabyte, you check the cluster status, just how you would if you did a local install, and then you explore YSQL by simply running that command, and then boom, you're in. That's really all there is. So let me just exit out here, and I can kind of show you Here I've got a 3-node cluster that I've got up and running on Kubernetes. You can see I've got my services here, 5433. We'll get into more of that in just a little bit in regards to connecting on what particular ports. But from here, I should be able to just go into my my Google Cloud Shell, and we'll do a little bit of authorization magic here to get the shell going. Right, so here, right, I've got my 3-node cluster running on GKE. To get to my YSQL prompt, right, I want to start developing some SQL. We call it, now we're at the SQL prompt, let's see what databases we have, or I should say what tables we have in this particular database. I've already got some tables there. And if this looks a lot like Postgres, it's because it is, right? At least the syntax is. I can change databases over to my sample database that I've already built called Northwind, and we'll just do a simple select, right? So that's a YugabyteDB cluster running on GKE that I'm already interfacing with that literally just takes a few minutes to install. It's super straightforward, super easy, just how I showed in those slides. So a bit of a segue, but I just wanted to show you how actually easy that is. Let's go back into presentation mode. Okay, JDBC. So if you're using like a third-party tool that uses a JDBC connector, or you have an application that needs JDBC, like I like using Airflow, for example. This is a Spring example, but most of these Java examples are very, very similar. It all looks the same, right? Like you were setting up a Postgres connection, because it is. We're using the Postgres driver. The only thing I'm calling out here is that when you're setting up your connect string, you want to use port 5433. Now, if you're a Postgres person, you probably remember that the default port for Postgres is 5432. So just increment it by 1. 5433, that's the YSQL port. It's essentially the TServer Service. That's the port assignment that it's giving to YSQL. That's really it, right? So if you're modifying your JDBC connect string to work with Yugabyte, and essentially if your tool works with Postgres, make the modification. There's a very high likelihood it's going to work straight out of the box. Okay, basic user management. I'm not going to show you how to do this in YSQL because it's pretty straightforward, right? Creating a role with privileges, creating a role with a password, setting up the password so that it expires, changing the user's passwords, listing all the users. If this looks like this is how it works in Postgres, you're absolutely correct, right? So I don't want to belabor the point here. It's super straightforward on how to work with this stuff. Databases and schemas, creating databases, switching to a database like I just showed you, describing a database like I just showed you, creating schemas, assigning schemas to users. It's all the same, right? There's nothing new to learn here. It's exactly how Postgres works. Creating objects and loading data from external files, it works exactly the same. And I'll show you exactly how this stuff works live. But what I'm trying to kind of convey to you here is that the look and feel is going to be like I'm interacting with Postgres. And that's our goal here. We want the barrier to entry for a SQL developer to be very, very low to start taking advantage of distributed data storage and all that good stuff that comes with a distributed SQL system. Right, here's our last slide before we jump into some exercises, just kind of laying the groundwork here, is that in my examples, I'm going to be using the Northwind sample database. So those of you that have been kicking around as long as I have know that Northwind is the default database that's shipped with SQL Server. So it's been around for a really long time. And what the database is, it's got a variety of different tables. And what it does is that it simulates an import-export company that deals in specialty foods, and it ships them around all over the world. So it's got suppliers, and it's got customers and employees. It's got products, orders, order details, right? It's a pretty good data set, right, that can kind of give you a feel for a typical company that's in the business of buying, sending, receiving orders, employees, all that good stuff. So it's a good database to have to work with. Okay, so let's jump out of this. And let's cruise on over to the command line here. All right, we'll start with the blue one. So the first thing that we'll do is that we'll make this a little bit visual. Let's go ahead, and I've already downloaded Yugabyte. I did that via that wget. You can do it in other ways, I suppose. And I've already unzipped it, and I've already navigated into the installation directory, right, which you can see here specified in the 2.3.2. So the first thing that we want to do, and I showed that in the slides, is let's create a 3-node cluster, right? And you can see that I'm doing that because I'm specifying RF3. So what do we need to know about the output here? Node count is 3. Replication factor is 3. Remember, we talked about our JDBC string. Only thing you really need to know about here is the port assignment. Again, it's 5433 versus 5422. And obviously, I'm connecting to node number 1 here, but obviously there's node number 2 and there's node number 3. The other thing that's pertinent here is if you want to look at the web UI that kind of ships with the database, that's where you're going to find it. So let me quickly come out of this and show you what that looks like here. Let's refresh that. Right, so here's the web view of the 3-node cluster that I just installed. Obviously, nothing is happening on it, right? It's not particularly interesting, but let's rectify that. Okay, so we've got that going on. The other thing that you can do here, this command that it shows you here, this status command, this can also be useful if you don't want to use the web UI and just want to, at the command line, get a quick heads up on what's happening with the database, right? So the new pertinent pieces of information that have gotten spit out are, we now have our node tells us whether it's up or running, all the connectivity information, node 2 is here, and node 3 is here, right? And that's the same information that we saw in the web UI. If we exit out of this full screen, I mean, look, we're running it locally on the Mac, but if we do say YB, search processes, we can see that our processes are here, right? We've got 3 T-server processes and 3 master server processes, right? So those are just 3 different ways that you can verify what's happening on your cluster, the processes, the services, again, that we talked about previously. All right, let's go back to full screen here. And Terminal does not like going full screen backwards and forwards. Okay, so we connected to the UI. Now let's get to a YSQL shell. All right, so again, now I'm in basically the SQL shell. I'm connected by default to the Yugabyte database. So let's build our sample database, that Northwind database that I talked about. So we create our Northwind database. And once that database is created, then of course we want to change to the Northwind database. Now we're connected to the Northwind database. And as I showed earlier, calling external files, right, to load data or to create objects is pretty straightforward. It's just how you would expect it to work. The one thing you want to point out here is that if you installed Yugabyte, go to the share directory, this share directory, and in there, you're going to find a variety of utilities and scripts, sample databases, etc. And that's where I'm pulling this particular script from. So there's nothing extra to download, just merely call that particular script. So let's go ahead and create some tables. I'm back to my prompt, which is at the very bottom. If I try to remember how to clear it in Postgres. Okay, cool, we're back at the top. So now we've got our database and it has objects in it. Let's go ahead and insert data into it. Let's see if we're quick enough. Maybe we can actually see some activity on the system. Yeah, cool. So we just did a refresh and you can see there's some reads and writes happening just from me building those database objects and loading data into it, calling those external files, right? So let's go ahead and go back to full screen. And once those inserts are done, let me see, how do we get back to the top? Clear. Right, so now I can see these are the database objects that were created in the Northwind database. Let's just do a quickie spot check. And you can see we've got data in it, right? Not bad. I mean, how long did that take? 2-3 minutes, and we've got a 3-node Yugabyte DB cluster installed locally. I'm at the YSQL prompt. I loaded a sample database, and now I've got data inside of it. Now, granted, some of you might say, ooh, working at the command line is so 1980s. Can we use some graphical tools? There's a variety of different tools that you can use, like pgadmin, Table Plus, IntelliJ, dbeaver, which is the one that I like, just because I started using it and I just kind of stuck with it. The other thing that's kind of cool is it does have native support for Yugabyte, but I'm going to show you how to wire up this SQL admin, SQL development tool using the Postgres driver. So I won't go native. I'll show you how kind of the compatibility works. So if you're using another tool that supports Postgres, I'll kind of show you how to wire it up. The mechanics are pretty much the same for all of these tools on how you set up connections. So let's find our connection that we want to use. We want to use Postgres, right? So we select Postgres, and when we set up our connect here, localhost, that's good. You could do 127.0.0.1 or .2 or .3, because remember, we have those T servers running on those different IPs that we could connect to those just as well. It's just about what node you want to connect to, and it's going to by default connect to node number 1, which is on 127.0.0.1. Port number, right? Our port assignment is 5433. Remember, the default for Postgres is 5422. Just make sure to flip this over to 5433. That's going to be your Yugabyte port assignment. Let's change our database to Northwind, which is the sample database that we built. Let's change our username to Yugabyte. There's no password by default. Obviously, like I showed you, you can set up some passwords. So yes, we are working with a local insecure installation of Yugabyte. Always good practice to test your connection. Yugabyte does not, well, it helps if I type correctly. How about that? Let's try, well, that's even worse spelling. Let's try this. All right, cool. So we're connected. You can see that we're using the Postgres driver to connect from this administration tool into a YugabyteDB cluster. So for all intensive purposes, this tool thinks that it's talking to Postgres, which is fine. That's exactly what we want. Okay, so now we have our connection here. I do want to make one quick edit to my connection, and that's specifically around how transactions are handled. And I want to do it auto commit after each line. Click OK. So again, now we're connected to this local Northwind database that we created, and we can just quickly verify under the public schema. Here's our tables, right? And we can do a quick, let's just do categories, view data, right? So you can see I'm now interfacing with Yugabyte through this third-party tool, which makes it a lot easier to kind of visualize data, work with data, especially if you're a visual person and you like these sorts of tools. Okay, so let's do some basic stuff. Let's build a table. Let's insert data into it. Instead of doing it via external files, let's go ahead and do that using the tool. So let's crack open a new SQL editor here, and let's create a table. We're going to create a table called promotions. Think too crazy sophisticated, some primary keys and some columns. So now we've created our table. If we refresh our Explorer tree, we should now see that table there. We see the promotions table is there. All right, let's put some data into it. So here we're inserting, looks like about 5 rows of data. Now, if I go back to the promotions table and I view the data, we can see that the data is there. Super straightforward. Really, all I'm trying to articulate here or demonstrate is that it's straightforward to get started with Yugabyte in a Postgres compatible manner. All right, let's get a little bit crazy here. Let's do some other stuff. Let's create a new script. Let's build a function, right? And in this particular function, what we're going to do is that we're going to count the rows of a table, right? So this function just goes out based on the schema and the table name that I specify. It just counts the number of rows and pulls them back. So here, all we're trying to show is that you can use functions like you would in Postgres inside of Yugabyte. So let's go ahead and run the function. It looks like our function ran, at least I hope so. So now let's go ahead and leverage it. So let's paste that here, and let's see if this works for us, right? 91 rows. 91 rows in what? 91 rows in the public schema customers table, right? So that's how a function is going to work in Postgres, and it's going to work exactly the same inside of Yugabyte. Let's do one more. And this time, let's do a trigger. So let's create first a table, and let's call this table customer audits. And what we want to do is that whenever somebody makes a modification to a customer's name, we want to log it. We want to log it to a table so that we can go back and look to see at what time a particular customer's name was updated. So we need to track that somewhere. So let's put that information into a table. All right, tables generated. If we refresh our Explorer tree, we should now see the customer audits table, which we do. Okay, so the next thing that we want to do is create our function, right? So let's create our function. And this function is pretty straightforward, right? All it does is basically captures the old name that before it was modified and puts it into the audit table. Okay, so now we've run that. And in fact, if you actually go to the Explorer tree functions, you can see those functions are there. Again, it's looking and it's smelling a lot like Postgres, because the third-party tool or this administration tool, it shouldn't care that it's talking to Yugabyte. Okay, so the next thing that we want to do is that we want to bind that trigger on the customer's table. So that looks like it worked. And then the last thing that we want to do basically to test that it all works is let's go ahead and update the customer's table, and we're going to change Mark, or we're going to set Carl's name to Mark, right? We're going to update the name of this particular customer. So now if I do a select star from that audits table, right? Because remember, it should have called that trigger, right? You can see here, the old contact name is there, Carl, right? So our trigger works as expected. And that's the long and the short of it, right? The point here is that if it works in Postgres, it should arguably work in Yugabyte. That's the point I was trying to drive home. Now we have a separate training that is all about YSQL development. This is really just to give you a flavor and a taste for how that YSQL works. Okay, cool. Now let's move on to the next part, which is going to be testing database availability. So if you want to try along at home, go to the docs /explore/fault tolerance. And in that documentation, it's a simple exercise where you can experience kind of what I'm going to show you, which is I'm going to start with an RF3 cluster, which we already have installed locally. I'm going to download and run a sample Java load generator. So it'll start generating some reads and some writes on the nodes. And we want to see that the load kind of balances out. No hot nodes, no hot shards, evenly balanced, steady state. And then we're going to remove a node, in this case, node 3. We're going to wait 60 seconds, which is kind of our heartbeat mechanism. We're going to flag that node as dead. And then what we want to see is we want to see that that node is still able to serve reads and writes, right? Because again, with RF3, I can tolerate the failure of one node and still be able to serve reads and writes. And we want to just kind of see how that works. And then we'll restore node number 3, see that the cluster stabilizes again, kind of balances out, and then we'll go nuts and we'll add a 4th node. We'll kind of do some scale out. So let's walk through this process live. Okay, let's open up this. So I won't go big screen. Hopefully that's big enough. Okay, so again, I'm in the Yugabyte directory, and all I need to do, again, if you're following along in those docs, this is exactly what I'm showing you, is first let's download the load generator. And then once I have the load generator downloaded, it's a simple Java program. Then I'm just going to pass it some variables. I'm going to specify, hey, what nodes do I want the load generator to work against? In this case, I'm going to have it work against all 3 nodes. And then I'm also going to specify the number of threads, write threads as well as read threads. And in this case, I'm going to specify 3 write threads, 3 write threads, and 3 read threads. Okay, so the generator is starting up, it's creating a table, it's doing its thing, and the output that we want to look for is this output, right? Which tells us, hey, here's the number of reads, here's the number of writes, right? And it's just spitting out the load, the status of the load or the metrics behind the load as it's running. So let me move this to the side, and hopefully this load generator won't completely kablamo my laptop with all the stuff that's running on it. But if we go back to our tablet server, you can see that now in our reads and writes column, things are starting to stabilize, right? Caches are starting to warm, all that good stuff. You can see that we have a fairly balanced read-write columns, right, across all three nodes. Okay, so now what we want to do is let's introduce some chaos or some calamity. So let's exit our YSQL shell, and let's remove node 3. And I can already see here my laptop starting to, CPU starting to burn. Okay, so now that we've stopped T-server number 3, or node number 3, if we refresh this, the thing that we want to spot here, again, node number 3, time since heartbeat is 14 seconds. There's a 60-second, that once it hits 60 seconds, it will be marked as dead and will be formally kind of ejected from the cluster. So we'll just keep tracking that till it hits the 60 seconds. In the meantime, what you're able to do, for example, if we wanted to go back and verify that in fact that node has gone offline, is again, if we do our status command, come here to node 3, we can see that it is stopped. I guess we could also do a cheapy verification in going to the activity monitor, and we can see here I've only got 2 T-server processes running, which makes sense, right? Because the node 3, the YSQL API, so to speak, the T-server process has actually gone offline. Let's refresh our view here. Okay, we're at 60 seconds. It's been marked as dead. You can see that there's no more reads and there's no more writes on that particular node, but we can see that reads and writes are still happening on the other 2 nodes, and they're fairly well balanced, right? Okay, so now what we want to do is, let's just say we figured out what the issue was. Now let's bring things back to a normal state. Let's go ahead and start node number 3 back up. So with node 3 back up, let's do a quick status check at the command line. Let's go to node number 3. You can see we now have a PID, which is good. If we refresh this, we can see that node 3 has now rejoined the cluster. Our reads and our writes are not completely balanced yet. We're replicating data back and forth, getting the node back in business. Okay, on this refresh, we can see reads and writes have once again stabilized across those nodes. Okay, so let's say we want to add another node, right? Like let's say we want to get ahead of this particular problem and add a 4th node. So adding a 4th node is as simple as this add node command, right? That's all we're doing here. We're adding it to the cluster. All right, so it looks like here in the output, you can see we've now got another T-server up and running. If I refresh my UI, we can now see that that node is there, right? And it'll take a little bit of time for that node to kind of get all the data that it needs and then fully start participating in the cluster. But you can see that it's already got some data in it and it's already starting to participate in it. And that's kind of the long and the short of it of how you can, I'm going to kill my load generator here before it completely destroys my laptop. And that's the long and the short of it of how you can go from a RF3, like a 3-node cluster, generate some load against it, remove one node from the equation, observe that you can still do reads and writes, bring the node back into the cluster, and see that the reads and writes balance across all 3 nodes, and then how you can add a 4th node to effectively scale out. So that's how you can test fault tolerance. Again, it's in the documentation. I just walked you through it. You can do it on your laptop or on your own environment as well. Okay, this last section, I know we're running a little bit long, is TPCC, right? So benchmarking specifically, let me go back to presentation mode. Go to the docs/benchmark, and there's a variety of different benchmarking tools that you can use. There's TPCC, there's Yahoo's YCSB, there's Sysbench, there's a key value workload, as well as benchmarking utilities for large data sets, right? Obviously, benchmarks are kind of silly on laptops. Benchmarks are more designed for environments where it looks like your production environment. That's where you're really going to get an idea for, is the system capable of doing the things that I am going to need it to do? But in any event, I did it just to kind of show you how it works. I did it on my Kubernetes and I did it locally. But in this case, I'm just going to zero in on the TPCC benchmark. I won't go into what it is. It should be, if you've been kicking around databases, you probably know what the TPCC benchmark is. And I think we've got examples for 10 warehouses, 100 warehouses, and I believe 1,000 warehouses. But if you want to do a quick 10 warehouse TPCC benchmark, it's super straightforward, right? Download the TPCC benchmark, unzip it, navigate into the TPCC directory, and then you can optionally run it step by step, which means that you can create the objects, you can load the data, and then run the benchmark, or you can do it all sequentially in a single command like I'm showing right there, which is basically create the objects, load the data, run the benchmark, and run it against these particular nodes, in this case, a 3-node cluster. And on the right-hand side, this is what you get in your output, right? You're going to get, when it kicks off, it tells you what it's actually doing, and then it spits out at a high level your metrics, and then you also get a CSV file with all the stats in it. You want to navigate to the TPCC directory /results, and in that results directory, you'll see a CSV in there that'll have all the juicy details about the benchmark. That's just an example. There's a bunch of other benchmarks that are in there that you can run at your leisure in your own time. All right, so now we are in the home stretch. It is time for our course review. And we'll do it a simple Q&A style. What is distributed SQL? At a minimum, a distributed SQL database has to have these 5 characteristics: a SQL API, automatic data distribution, automatic replication of data synchronously in a strongly consistent manner, support for distributed query execution, and support for ACID transactions. That's what distributed SQL is all about. What is Yugabyte? Yugabyte's architecture and design is inspired by Google Spanner. It has a YSQL API that is compatible with Postgres 11.2. In regards to the CAP theorem, Yugabyte is a CP database. Yugabyte's YSQL API supports 2 isolation modes, serializable and snapshot. Yugabyte is completely open source. It's released under the Apache 2.0 license. Yugabyte supports advanced RDBMS features like triggers, stored procedures, foreign keys, and some Postgres extensions. And all transactions in Yugabyte are guaranteed to be ACID. That's what you need to know about what Yugabyte is. All right, what is the difference between distributed SQL and a monolithic system? All you got to remember is that traditional monolithic RDBMSs, you have to scale up to get more capacity, basically throw hardware at the problem, while distributed SQL systems, you add more nodes to get more capacity. You essentially scale out. What is the CAP theorem? It states that in the face of a network partition, you can only solve for either availability or you can solve for consistency. Those are the 2 options that you have. What is Raft and how does Yugabyte make use of it? Raft is a consensus algorithm. Yugabyte uses Raft to create consensus between tablet peers. Tablet peers are merely tablets that hold, or shards that hold, the exact same set of data. They need a leader, they need a follower, they need a mechanism for being able to determine when it's okay to write a change to storage. What are the main components of Yugabyte? We've seen a lot of these in action. You've got nodes, right? Nodes can be VMs, containers, bare metal. You've got these nodes that are put together to form a cluster or a universe. These clusters have 2 services that are running: your TServer service and your master service. Your TServer service is what's going to be responsible for hosting and serving data. Your master server process is going to be all the metadata, system-wide operations, backups, security, all that good stuff. That's going to be happening in the master service. What forms of replication does Yugabyte support? 2. Internally within the cluster, node to node, synchronous. If you want to replicate from cluster to cluster, that's going to be asynchronous replication. What is DocDB? DocDB is YugabyteDB's document data store. It's based on RocksDB that we've extended and forked. That's going to be your data layer. That's how Yugabyte delivers distributed data storage. How does sharding and data distribution work inside of Yugabyte? Database sharding, again, is essentially the horizontal partitioning of rows. And then you take those shards, right, or those tablets, and you spread them across nodes. The whole idea here is that by doing so, we increase both read and write scalability. Yugabyte is going to shard data by primary key. There's 2 modes in which you can shard data, either by hash or by range. Remember that tables are being split into tablets. and these tablets are being replicated synchronously within the cluster. Because it's not good enough to just basically shard data, you also have to replicate it. And that's how sharding and data distribution is going to work in Yugabyte. What APIs does Yugabyte support? 2, YSQL and YCQL. YSQL is the Postgres compatible API. YSQL is the semi-relational API that's inspired by Cassandra. How do distributed SQL databases tolerate failures? They shard data, and at the end of the day, no single node has all the data, right? You can always reconstitute the database from other nodes. That's how it achieves fault tolerance. What's a network partition and how does Yugabyte handle them? Network partition, again, is just going to be where, although clients can talk to the nodes, there's a certain set of nodes within a cluster that can't communicate with each other. You can imagine if they can't talk to each other, but clients are writing data, you can lead to inconsistencies super fast. What Yugabyte does is that basically it will take nodes that are not in the majority, boot them out, and nodes that can achieve some consensus, those will be online and be able to accept reads and writes. What are secondary indexes and why are they advantageous to use in Yugabyte? Number 1, it gives you another way for being able to do fast lookups on data other than your primary key. It also helps you enforce the uniqueness of columns. What formula helps us determine the replication factor that we need to use to achieve a fault tolerance of a particular type of nodes? RF factor equals 2 times the fault tolerance plus 1. So in the scenario of we want to achieve a fault tolerance of 1, meaning we can lose 1 node and still be online to serve reads and writes, that would be 2 times fault tolerance of 1 gives us 2 plus 1 gives us 3, which means we need a replication factor of 3. What are co-located tables? This is an advanced feature that allows you to basically stuff a bunch of tables into a single tablet so that there's just less overhead, less metadata, and it gives you a much faster, more compact access. What is change data capture? It's an advanced feature in Yugabyte that gives you a mechanism for being able to stream changes that are happening in the database to other systems, other databases, logging facilities, things like Kafka. Okay, this is it. What are the next steps? Study guide. If you're listening to me right now, you will be emailed a link to download the study guide. The study guide is going to cover everything you need to know to pass the exam. So if you sat through the presentation, if you installed, if you read the exam prep guide, you're going to do well. You're going to be fine. Certification exam. If you're listening to me now, you're going to get emailed a link to take the exam. The exam consists of 37 multiple choice questions. You need at least an 80% to pass, and you are allowed to retake the exam as many times as it takes for you to pass. My suspicion is that everyone will pass in the first or the second try. Your results are going to be available immediately. And what about my certification and badge? Everyone who passes the exam will be emailed a certificate and a badge. Check your inbox in the next 24 to 48 hours after completing the exam, because I got to create those, and I'll get them out to you. I'll do my best that I possibly can. Asking, is there upcoming courses? Yes. So we just went through the YugabyteDB Fundamentals, which is just to get your feet wet in distributed SQL. But we do have a YSQL development course, a YSQL development course, YugabyteDB Fundamentals. So this dives really deep into installations on different environments, multiple clouds, playing with RF factors, doing backups, restores, doing security, growing clusters, doing all kinds of killing processes, doing all kinds of bad things to the cluster, and how to kind of recover from all that. So there's a separate course that just dives deep on that. And then the other one that I'm excited about is Jamstack development with Yugabyte. So it mostly focuses on microservices development, basically building a shopping cart on top of the Northwind database that we just showed, using Jamstack, some GraphQL as well, using YugabyteDB as a backend. So it's not so much about Yugabyte, that particular course, it's more about the actual Jamstack development. That's the one I'm excited about. But all these are upcoming courses. Stay connected to the meetup, stay connected in the training channel. That's when you'll find out when these things are happening. Of course, they're all free. We encourage everyone to sign up for them. Okay, I may sound like a broken record here, is that if you've got questions, make sure to sign up for the Yugabyte Slack, join the training channel. That's where I'll be hanging out today. answering questions, following up. If you've got technical questions about the certification, the exam, upcoming classes, all that good stuff, just jump into that channel. I'll do my best to answer everyone's questions. We can take conversations one-on-one if it makes sense. Again, oh, I forgot. Make sure to vote for the charity. It's in the Q&A, but it should be in the training channel as well. If not, I'll post it in there as well. Make sure to take a few seconds out, vote for your favorite charity. It definitely helps us out in doing something nice for other people instead of just thinking about ourselves. So it helps out in distributing love there. So I want to thank you, everybody, for taking time out of their day. I know we ran a little bit long, 15 minutes long, but I appreciate your patience. Hopefully you found it useful. Thanks, Karen. Thanks, everyone at the meetup for helping set this up. And we hope to see you soon in a training or in the Slack. And again, reminder, give me less than 24 hours to send one email as opposed to a bunch. In the email, I will have a link to the recording, a link to the exam prep, a link on where to take the exam, so you can kind of get it all in one communication. And then as you finish the exam, again, give me 24 to 48 hours to send you your certificate and your badge, and then we'll just go from there. So thanks, everyone. I appreciate your time. Stay safe, stay sane, and we'll see you at training next time. Thanks, everyone. Bye.